Please be reminded that we are still discussing how to reduce the noise effect with hysteresis. The upper figure will show the input waveform and the triggering points, while the lower figure will show the output waveform. Let's assume that the initial output voltage is at the positive saturation. This positive saturation will feed back to the non-inverting terminal and give the upper triggering point. That is this green line, while this pink curve is the sinusoidal input signal applied to the inverting terminal. So Vin is equal to V negative, while V positive is equal to the triggering points. During this period, the V positive is higher than the V negative, so that's why the output stays high. But when the input signal goes higher than the upper triggering point, the V negative is higher than the V positive now. That causes the output to switch from high to low. And this change in the output forces the triggering point to switch from upper to lower. During this period, the V negative is higher than the V positive, so the output stays low. But when the input signal goes lower than the lower triggering point, the V positive becomes higher than the V negative, and this change forces the output to switch from low to high. And this change in the output forces the triggering point from lower to upper too. During this period, the V positive is higher than the V negative. That's why the output stays high. And similarly, when the input goes higher than the upper triggering point, the output switch from high to low, while the triggering point switch from upper to lower. We have just discussed that the Vin is equal to the V negative, while the V positive is equal to the triggering point. During this time duration, the V positive is higher than the V negative, so the output stays high. That will change when the input signal goes higher than the upper triggering point. Then the V negative will be higher than the V positive, so the output is forced to switches from high to low. And this switch in the output will change the upper triggering point to the lower triggering point. And this change is the key point about how the noise effect can be reduced. Now, the triggering point is so low, it is impossible for the input signal to cross over the triggering point, so no further triggering to occur, and the output stays low so long as the V negative is higher than the V positive. When the input signal goes lower than the lower triggering point, it will become the V positive higher than the V negative and causes the output to switches from low to high. And again, when the output switches from low to high, the triggering point also switches from lower triggering point to upper triggering point. And this change in the triggering point will prevent the input signal cross over it unnecessarily. So, a small amount of noise has no effect on the output. And a comparator with this hysteresis feature is called a Schmidt trigger. The amount of hysteresis is defined to be the upper triggering point minus the lower triggering point. We are going to calculate the upper and the lower triggering points for this comparator circuit with hysteresis triggering. The saturation voltage is given to be positive and negative 8 volts. The triggering point can be calculated by the potential divider formula. For the upper triggering point, we substitute the positive 8 volt, so the answer is 4 volts. While the lower triggering point, we substitute the negative 8 volt for the voltage here, the answer will be negative 4 volts.